Suppose that we have a square with a side length of 2, and we want to find its area. The question we're really asking is, 2 times 2 equals what number? 2 times 2 equals 4, meaning that the area of this square is 4. Let's imagine we have the same square, except this time we only know its area. So this time we're really asking what number times the same number is equal to 4. So what number times the same number equals 4? We know with the law of exponents that this simply means s squared, and the other side is still equal to 4. So what number times what number equals 4? We know that the only number that can be true for this is 2. The only positive number that makes the square with an area of 4 is 2. So from a square with an area of 4, how did we get to the side length of 2? So let's highlight this. How did we get this part? We can say that the number 2 is the square root of a square with an area of 4. So what if we could take the square root of any number? So square root of number. We want an operation or a symbol that means take the square root of the number. There actually exists one, and mathematicians have decided to use this symbol to mean take the square root of the number. So let's rewrite the equation we just solved. S squared equals 4. By taking the square root of both sides, we would be left with the square root of 4 equals 2. And we can quickly verify this by creating a square with an area of 4, meaning that each side would have to have a length of 2. Now let's say we have a square with an area of 25. We can call the side length of this square s. In other words, we want a number that when multiplied by itself gives us 25. We can rewrite this as s squared equals 25. Remember that we can take the square root of each side here. So we would have square root of s squared equals the square root of 25, meaning that s should equal 5. What does this mean? This means that if we replace the side lengths here with 5, we would get a square with an area of 25. This is because 5 times 5 equals 25. Now let's say we have a square with an area of 9. We're going to call each side s. And again, we can set up an equation that says s times s equals 9. So what number times what number equals 9? We will rewrite this as s squared equals 9, and we can take the square root of both sides, meaning that the side length is equal to 3. We can check this by putting these side lengths here, and knowing that 3 times 3 equals 9. Now we have a square with an area of 36. We know that there's a number that when multiplied by itself should give us 36. If we take the square root of both sides, we should get s equals 6. This means that in the square, each side length should be 6, because 6 times 6 equals 36. We now have a square with an area of 16, and we want to find two numbers that when multiplied by each other gives us 16. This number would be 4, because 4 times 4 equals 16. Same concept here. We want two numbers that when multiplied by each other gives us 49. This number would be 7, because 7 times 7 equals 49. What two numbers when multiplied by each other give us 100? This would be 10, because 10 times 10 equals 100. Finally, what two numbers when multiplied by each other give us 1? This would be 1, because 1 times 1 equals 1. Using a similar process, we can rewrite each problem this way. We know that 7 times 7 is still 49. We know that 10 times 10 is still 100, and we know that 1 times 1 is still 1. So let's go ahead and break down the square root of 7 times 7 into two square roots. So we would have square root of 7 times the square root of 7. Notice how in the previous problem, since we multiplied the same square root by itself, in other words, the number inside the root is the same, we simply took this number out and got it as a result. Why? Two square roots, when multiplied by themselves, cancel out. This means that if we're multiplying the square root of 7 by the square root of 7, these two will cancel out, meaning that our answer is 7. And we know that's true because in our original problem, we said that the square root of 49 is simply 7. Likewise, in this problem, we can break down 10 times 10 into the square root of 10 times the square root of 10. We know that these two square roots cancel out, so our answer would be 10. And now, we can break down the square root of 1 times 1 into the square root of 1 times the square root of 1. And as these two cancel out, we know that the answer is simply 1. Now, why would we want to use this process? We have numbers such as 32 that don't have a perfect square root. This means that when we draw a square and we have an area of 32, there is no exact side length that would give us 32. In other words, there is no integer number that would give us 32 when squared. You know that 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and that 6 squared is 36. Notice how it should be in between these two numbers. So let's apply the process we just did to attempt to have a solution that is closest as possible to this. We can apply the same process in this problem because we know that 4 times 8 is 32. Except that we know that 4 is really 2 times 2, and that 8 is simply 2 times 2 times 2. we have a total of 5 2's. So we can break this down into 5 individual square root 2's. So now let's simplify it. Square root of 2 times the square root of 2. It is the same square root being multiplied by itself, which means that it would cancel out and give us 2. Same process here. Square root of 2 times square root of 2. We know it's the same square root, so we're left with 2. And we bring down this multiplication sign, so there. And now the square root of 2, we can't simplify that any further, so it would mean that we have 8 times square root 2 left over. We can now simplify this as 4 square root of 2. And this is as far as we can get into simplifying the square root of 32. Now we have 4 squares with an area of 20, 27, 55, and 80. The side length that would correspond to a square with an area of 20 is not perfect, because we know that if a square has a length of 4, its area is going to be 16. And we know that if a square has a length of 5, its area is going to be 25. So the square root of 20 lies somewhere in between these two numbers. So we can call this a non-perfect square, because its side length is not going to be an integer value. It's not going to be a whole nice number like this. We know that we have 4 non-perfect squares, meaning that we have to apply the previous process to simplify each square root as much as possible. Let's start off with the square root of 20. The square root of 20, we know that this is equal to the square root of 5 times 4, because 5 times 4 is equal to 20. We can still break this down into 2 square roots. Square root of 4 times the square root of 5. The order here does not matter. We know that the square root of 4 is a perfect square, and its value is 2. So its value is 2. We know that square root of 5 is a non-perfect square, and it would lie somewhere in between 2 and 3. In other words, we can't simplify it as it is. So our answer would be 2 times the square root of 5. Same process here. We know that the square root of 27 is simply equal to the square root of 3 times 3, which is 9, times 3. 9 times 3 is 27. So we know that 3 times 3 times 3 is equal to 27. Let's break this down into individual square roots. This would be the square root of 3 times the square root of 3 times the square root of 3. We know that since we have 2 of the same square roots, the square roots would cancel out. So we're left with 3. In the square root of 3, it is once again a non-perfect square, and it would lie somewhere in between 1 and 2. So we're left with 3 times the square root of 3. Same process with the square root of 55. We know that the square root of 55 is simply a square root of 11 times 5. 11 times 5 is 55. So let's break this down into 2 square roots. Square root of 11 times square root of 5. Notice how square root of 11 and square root of 5 are non-perfect squares, because the square root of 11 would lie somewhere in between 3 and 4. And the square root of 5 would lie somewhere in between 2 and 3, like we previously said. As we cannot simplify anything in this problem, we would simply write down the original expression, square root of 55, as it cannot be simplified. Cannot be simplified. Square root of 80. We know that square root of 80 is equal to 10 times 8, because 10 times 8 is 80. Let's break this down into two square roots. Square root 10 times the square root of 8. Well, we know that we can rewrite this as 5 times 2. We can also rewrite this as 2 times 2 times 2. Notice that we have 4 2's. 4 2's and only 1 5. So in other words, this is the same thing as the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2. And then since we have 1 square root 5, you would write down times square root 5. All we did was break down 10 into 5 times 2 and 8 into 2 times 2 times 2. So we rewrote all of these factors as individual square roots. We know that this evaluates to 2, as the square roots would cancel out. This portion right here also evaluates to 2. And square root 5 is a non-perfect squared, meaning that it cannot be simplified. Cannot be simplified. So what are we left with here? 4 times the square root of 5. 4 times the square root of 5 is equal to our original problem, square root 80. And it would be our answer as we simplified it the most we could. Now we have 3 non-perfect squares, and we're going to apply the same process to simplify them. We know that the square root of 90 is equal to the square root of 9 times 10, because 9 times 10 is 90. So we can break this down into the square root of 9 times the square root of 10. We know that the square root of 9 is equal to 3, as it is a perfect square, and that the square root of 10 is a non-perfect square. So we're left with 3 times the square root of 10. Now we have the square root of 68. We know that the square root of 68 is simply equal to 34 times 2. We can break down 34 into 17 times 2. So we know that this entire thing is equal to the square root of 2 times the square root of 2 times the square root of 17. 2, 17. This right here evaluates to 2, and the square root of 17 is an imperfect square. So we're left with 2 times the square root of 17 as our answer. Now the square root of 200. We're not 200 is really 100 times 2. We can break down 100, but it is more convenient if we write square root of 100 times square root 2. This is true because we simply broke down the original expression into two square roots. We know that square root of 100 is 10, as it is a perfect square, and we know that the square root of 2 is an imperfect square, so the answer must be 10 times the square root of 2.